Dr. Stephen Koch is a professor of chemistry. He got his BS from Fordham University and his PhD from Massachusetts Institute of Technology, and then did postgraduate work at Texas A&M and Cornell. He and his wife Jane have recently bought a house in Chautauqua and hope to spend more time here in future years. He's speaking today because he says his wife made him do it. So we thank his wife for making him do it. And you can see his topic for today will be a discussion of some inorganic chemicals and how they have been seen as transition metal complexes. So with that, I'll turn it over to Dr. Stephen Koch, and please welcome him to Chautauqua.
Okay, welcome. It's pronounced Koch, like Mayor Koch in my family. It's we're a synthetic chemists, okay? We're interested in how metals function in biological systems. Robert chose a more conservative title. I could have given the talk, why is the product of the reaction first done by Dr. Frankenstein of green vitriol with a lye of blood, one of the ingredients in the table salt that I bought at Wegmans last month? Okay, it's I'll fill you in on this as they go along. We're doing chemistry of iron with cyanide and carbon monoxide carefully. Okay, it's over the years. I've been supported a little bit by the National Science Foundation, so your taxpayers' dollars, and the Petroleum Research Fund. It's why should biochemists or chemists be interested in transition metals? Because about 35% of metalloenzymes and proteins contain 35% of enzymes and proteins contain metals. And there are examples from just about the whole first row of the periodic table, and then some second and third row elements. I show a hypothetical metal center in a metalloprotein. These are the side chains of amino acids. I've cut away the rest of the protein. Okay, so you could have let me get my mouse, a tyrosine, an imidazole of histidine, carboxylic acid, glutamic acid, aspartic acid, methionine, cysteine. It's and then there are, of course, other centers. Okay, this is one which we have been particularly interested in over the years, iron sulfur centers in proteins. So there's a 4 iron, 4 sulfur cluster in many metalloenzymes and proteins, 2 iron, a 1 iron system, and a 3 iron, and more complicated systems. We got involved in the chemistry I'm going to talk about when they discovered the structure of the enzyme hydrogenase. Hydrogenase enzymes are present in certain bacteria and archaea, and they catalyze the reaction of protons and electrons to make hydrogen. It's this is a reaction which occurs in fuel cells, but in fuel cells you need platinum electrodes. Nature has figured out how to do this, what we call earth abundant elements. It's nickel and iron. And this is the structure of the active site of the nickel iron hydrogenase. It's there's a nickel bound to the protein through 4 cysteines. It's and then there was a mixed metal cluster. Was totally surprising, was bound to the iron with 2 molecules of cyanide and 1 of carbon monoxide. These are native ligands. Okay, but ligands are those things which bind to metals. Everybody knows cyanide and carbon monoxide are deadly poisons. Okay, it's so when we approach a problem, this was a total surprise when this was reported, and so we said, "What we want to make compounds like this," and we have, okay, to try to produce the reactivity. Okay, it's and maybe we could bind them to a graphite electrodes, and maybe they would act as platinum. That hasn't happened, but we saw cyanide and carbon monoxide. So we asked, what's known in the inorganic chemistry of compounds with iron, with both iron with both carbon monoxide and cyanide. It turns out, even though 15% of transition metal compounds, which are in the structural database, have a CO, it's the favored ligand of inorganic chemistry, and cyanide is the oldest ligand, which we'll see about in a second. There were only 3 compounds known when we started. We very happily reinvestigated this compound, which was first made in 1887. When I knew more about the history of chemistry when I was 16 than I did when I was 55. I thought before World War II, they discovered the elements. And if you're going to talk about the chemistry of cyanide and iron, you have to talk about Prussian blue. Prussian blue was first made in 1704. You take iron 2, react it with 6 cyanides, you get ferrocyanide, which is iron 2, 6 cyanides, 4 minus. This is a virtually colorless compound. You react it with iron 3, which is a light yellow, and you get an intensely blue solution, out of which you can isolate Prussian blue. This was the first man-made pigment. Okay, it's the iron 3s bind to the nitrogen ends of the cyanide. It's and you get this 3-dimensional cluster. Well, I was interested in this because I go, who are the people who did this first synthesis of Prussian blue? Because it's probably the first example of synthesis. Okay, it's a big thing in chemistry. Chemists create their own world. We make compounds which we can study. Well, it turns out Prussian blue was first made in 1704 by this gentleman, Conrad Dippel and Diesbach. Okay, they didn't publish it. It was an immediate commercial product, and if I had time, I could show you artwork right soon after 1704, which used Prussian blue as a pigment. Well, they didn't publish it. John Woodward essentially stole the synthesis and published it in 1724 in the Philosophical Transactions of the Royal Society. Well, when I first saw this, I figured, oh, well, Diesbach and Dippel were acting in Berlin. It would have published in German. Philosophical Transactions of the Royal Society is going to be in English. And when my library got it for me, okay, here's the prep. Okay, I went to Fordham, so I had a classical education, took Latin in high school. So I recognized this is Latin. It's I'll show you the first page of the synthesis of Prussian blue. Preparation of Prussian blue sent from Germany to John Woodward, professor of medicine at Grissom College. He was a member of the Royal Society. He was actually thrown out of the Royal Society later. Take 4 ounces of crude tartar, 4 ounces of dried crude nitra, powder them minutely and mix, detonate them with charcoal. When this salt is still hot, 4 ounces of finely powdered oxblood is added. It's put on a fire and the crucible is piled round with coals so that it can gradually begin to glow and the material take fire. Have ready 2 pints of boiling fresh water into which the material is thrown while still glowing. They say Diesbach and Dippel accidentally discovered Prussian blue. Okay, if this was an accident, what the heck were they trying to do? The thing is, they didn't have any cyanide containing starting material. It's beginning of the 17th century, the 18th century, 1704, we have alchemy. Then we come to one of the greatest chemists of certainly the 18th century of all, in fact, of all time. In late 18th century, he figured out the synthesis of Prussian blue, and in the process synthesized hydrogen cyanide, potassium cyanide, and potassium ferrocyanide. In his introduction, he says, everybody understands, he references Diesbach and Dippel. It's everybody knows how to make the lye of blood. So that caught my attention. And in fact, what the pyrolysis reactions and things were making potassium carbonate. When Diesbach and Dippel pyrolyzed potassium carbonate with dried oxblood, the carbon and the nitrogen of the protein became the carbon and nitrogen of potassium cyanide. They quickly realized any source of protein would work. And it's in fact, the iron doesn't come from the oxblood. Later in the prep, Well, that's what's called the lye of blood. Later in the prep, they add green vitriol, which is iron sulfate. And so what Diesbach and Dipple were doing, were reacting iron 2 with cyanide. And I say this is the oldest reaction in synthetic chemistry. And chemists like to name reactions after the people who first did it. So I call this the Diesbach-Dipple reaction. Well, this is just showing you, okay, ferrocyanide from one of our own crystal structures. When you see a nice, pretty picture with labels, that means this is crystal structure we did. Of course, ferrocyanide has been known for a long time. And in fact, ferrocyanide is so inert to substitution that it's an approved food additive. It's once the cyanide ligands go on to iron, they don't come off. And in fact, if you look at one's kosher salt, okay, the ingredients are salt and the yellow prussate of potash, the yellow prussate of soda, okay? And that's in fact of sodium ferrocyanide. They add it as an anti-caking agent. You wouldn't sell much salt if you listed salt and sodium ferrocyanide. Okay, well, I was happy last winter when I was in Wegmans. Wegmans is one of the great things about living in Chautauqua. They also add yellow prussate of soda as an anti-caking agent. Okay, and again, this is sodium ferrocyanide. It's only present in low amounts, but still, and it's been reevaluated. It's just not poisonous. The cyanide holds so tightly to the iron and ferrocyanide that it doesn't dissociate. If you ate it, it will come right out the other end. Well, as I say, we reinvestigated this compound, which was reported in 1887. Potassium 3, iron, 5 cyanides, and 1 CO. It was impurity in a commercial process to remove hydrogen cyanide from coal gas. Okay, now they actually wrote it in 1887 with this formula, but they were challenged when it came to the structure. They proposed a structure shown on the left based on what they thought was the structure of ferrocyanide. This is before Alfred Werner had established the stereochemistry of octahedral complexes. We did the crystal structure and confirmed what Alfred Werner had predicted more than 100 years ago. Okay, we got a JACS communication from this work. JACS is the Journal of the American Chemical Society, is the most prestigious journal of chemistry. Okay, if you can't get into science and nature and you're a chemist, JACS is the place to go. And I'm not going to talk about what we learned about the compound, except it has to do with the synthesis. It's this compound, because ferrocyanide is so inert to substitution, they start with ferrocyanide, oxidize it with nitric acid to make nitroprusside, which is in fact a commonly used drug for treating high blood pressure in the hospital. They displace the NO with ammonia and then replace the ammonia with CO. The person I postdoc for at Texas A&M back before I did couldn't get this reaction to work. So they took ferrocyanide, CO, at 300 degrees in water, at 140 atmospheres of CO. And after a day, they were able to replace one of the cyanides with CO. This is just an indication of how ferrocyanide is just so inert to substitution. Heber and Cotton were certainly people who could have won the Nobel Prize. You might ask, why did they go to all this trouble and not try the simple reaction of just reacting iron with cyanide and CO? Well, we wanted to make compounds with more COs. Okay, the enzyme has 2 cyanides and 1 CO, but so we thought if we started with a compound where CO was already bound to iron, reacted with cyanide, the cyanides wouldn't rip off the COs, and maybe we'd get a compound with more than 1 CO. And in fact, we got this compound, very simple compound, it never been made before. It's but we only had a very small amount. When we looked at we got crystal structure. When we looked at the solution at the vibrational spectra, which I won't, this is the vibrational spectra of the compound. I won't talk about it. But in the solution reaction mixture, there was none of the product. So we had a compound in 3% yield. Okay, it's a new compound. My postdoctoral advisor would have called it butterfly collecting. You're a synthetic chemist. You want to say you know how to make a compound. So we tried all sorts of ways. And then we decided, well, we'd be idiots if we didn't try the simple way. And in fact, we can make this compound in high yield by just reacting iron 2 chloride or sulfate, adding right open in the air with 4 equivalents of potassium cyanide as we bubble CO through the solution. And in fact, when we reacted with 5 equivalents of cyanide in water, bubbling CO through the solution, we get the compound with 5 cyanides in a CO. The simplest possible reaction led to these compounds. Well, it turned out this is the reaction of iron with cyanide, is what Diesbach and Dippel did in 1704. For the next 300 years, nobody had ever made another compound but ferrocyanide, or from ferrocyanide, Prussian blue. So there's a lesson to synthetic chemists. Don't think because you read the literature and try the simplest reaction. I still don't really understand. I can rationalize what people, I think, thought is if you reacted iron with 6 cyanides, you get ferrocyanide. If you react iron with less than 6 cyanides, all of the cyanide would go on half of the iron, and then the remaining iron would link it into Prussian blue type structures. Well, that's not the case. And we could make compounds with 3 COs and 3 cyanides, or the other isomer. The compound we first made had the COs trans to each other. We could make the cis isomer. And this goes back to history. Alfred Werner in 1890 established the octahedral structure of transition metal compounds when he had isomers. If you have a cis and a trans isomer, and that's the only isomers, then that suggests an octahedral structure. Okay, and he could have done the work we did, okay, more than 100 years later, okay, but he didn't. So we have developed Alfred Werner chemistry, which is the basic of coordination chemistry, 100 years later. Okay, and this is just showing you, here was the compound we got out of doing the reaction in water. We got the trans isomer, that's the COs are trans, and under certain other conditions, okay, we got the cis isomer. Okay, and it turned out it wasn't something special about carbon monoxide. We could make other compounds with 2 pyridines, both iron 3 and iron 2, which is doing reactions with right out in the air with 4 cyanides in pyridine solution, and we get these compounds. Okay, never been made before. Okay, do the reaction with 4 cyanides, iron 2 in dimethyl sulfoxide. Get the compound with 4 cyanides and 2 dimethyl sulfoxides. We only have a compound if we can get a crystal structure. That proves it. And we study other spectroscopic information, okay? But so here's the iron 2 compound with 2 pyridines, which is cis to each other, both in iron 3 and iron 2. It's with DMSO, is dimethyl sulfoxide. First of all, the iron coordinates with the sulfur of DMSO, okay, and we get the trans isomer. And we can study these compounds by NMR spectroscopy, vibrational spectra, etc. Never been made before. It's well, in 2019, okay, we got this great report from Karen Smith and Michael P. Callahan. They study carbon compounds on meteorites. Carbonaceous chondrite meteorites, they have discovered more, not them, lots of people, more than 600 organic compounds. Well, they found 2 transition metal compounds in their mass spec. Okay. Oh, there's Karen. Okay. And they're the 2 compounds. This was the one on the left was the one we had made for the first time. And the one on the right is the one we studied, which was first reported in 1887. Okay, it's so I thought this is a fantastic result. Okay, it's as far as I know, these are the first transition metal complexes. Now, of course, moon rocks, okay, a solid state and contain transition metal compounds, but these are molecular complexes, and they suggested that these compounds might be storage for cyanide. Turns out from hydrogen cyanide and CO, you can make almost anything, all the amino acids, which could lead to prebiotic synthesis of proteins, the purines and pyrimidines, which are present in DNA and RNA. So it could turn out that these are very important compounds, our compounds in the creation of life. Okay, it's so I think this is the neatest thing as I retire. It's I'm going to be studying when they hired one of my students as a lecturer, and we're going to study. All of a sudden, our chemistry is going to be more interesting. It's and more than we would like it to be more than cyanide storage. Remember, hydrogenase enzymes contain cyanide and carbon monoxide as ligands. Maybe these were compounds involved in the first creation of those centers, and also would like it if it's possible that these centers acted as catalysts, prebiotic catalysts. This is a picture of the theory that meteorites with these organic compounds and our transition metal compounds came to Earth, and this is how Earth life was created on Earth. It's okay. This is sort of neat. Okay, NASA has sent a probe to the asteroid Bennu. Okay, and they recently took a sample of the out of the asteroid, and on September 24th, 2023, they're going to return a capsule, re-enter Earth atmosphere, and land. And the people who studied found our compounds on the meteorite are going to be testing the this asteroid. Okay, and then to talk about catalysts, is we want our compounds to show reactivity. Okay, so if we have our di-DMSO compound with carbon monoxide, we can selectively replace 1 or 2 of the COs. Okay, and with the bipyridine compound, here's just showing you, we replace 1 of the pyridines with CO. And we're going to be reinvestigating these compounds as catalysts. Okay, this is just shows you the di-CO compound is inert to substitution. Okay, it took boiling water to replace 1 of the COs with cyanide. In the well, this is imidazole. Okay, the imidazole CO compound shows slow exchange of the pyridine or imidazole. So this is coming on and off, and maybe substrates could bind. When we have 2 pyridines, there's rapidly exchange of pyridines. And this is what we could conceive of. Here's the iron nickel hydrogenase, and maybe we could show that these iron cyanide compounds, simple cyanides, would reproduce some of the reactivity of the enzyme. Okay, these were my students. Okay, here's a picture a while ago. It's but I wanted to tell you, okay, about what I found about the people, the first synthetic chemist, Conrad Dippel. I found this from the Travel Channel. He was born in the castle Frankenstein near Darmstadt. Prussian blue wasn't his most famous discovery. Dippel's oil was, which he claimed as a universal medicine prepared by distilling the blood and horns and bones of deer. Well, why settle if you're going to use animal bones like ox blood? Why not use human blood and bones? Where would you get them from robbing cemeteries? In 1733, he announced he discovered a substance that would enable him to live to an age of 135. Okay, he died the next year. Well, there's an author in search of Frankenstein who exploring the myth behind Mary Shelley's monster. And it's sort of summarized on the back that Frankenstein's monster spring full blown from Mary Shelley's, let me see, my thing is in the way here, imagination that rainy summer of 1816. Or was he just produced as a competition to write the best ghost story? Or did Percy Shelley's wife piece together the tortured creature from the myth and mystery that surrounded the accursed family Frankenstein and the infamous alchemist who performed his diabolical experiments in their castle? Well, this is the same Conrad Dippel who synthesized Prussian blue. Oops, why doesn't want to go on. Okay, so here's Mary Shelley's inspiration for the character of Dr. Frankenstein is with first synthetic chemist. So I say Conrad Dippel, okay, was Dr. Frankenstein. And so his reaction, Diesbach-Dippel reaction of iron 2 plus cyanide could be called the Frankenstein reaction. It's but I don't want to leave you with this sort of chemistry because I want to tell you, just briefly outline Carl Scheeler, who's the person who figured out Prussian blue. And this guy was an incredible chemist. He discovered oxygen before Priestley and Lavoisier, but didn't publish. But don't matter. He discovered elemental chlorine, elemental manganese. He didn't isolate molybdenum metal and tungsten metal for the first time, but he isolated molybdate and tungstate. Arsenic. Look at this series of compounds he investigated. HF, H2S, arsine, hydrogen cyanide, potassium cyanide. Newton showed that light was broken up into colors. He showed that the energy of the light, different light was able, high energy light was able to reduce silver and low energy light was not. He isolated for the first time tartaric acid, citric acid, lactic acid. He was just a Swedish druggist, okay? He didn't live that long. And when you read his paper on Prussian blue, you can understand why. He reports tasting and breathing hydrogen cyanide. But his paper on Prussian blue, it has to be translated into modern chemistry, but it reeks of the scientific method, okay? It's okay, and that's, I think, is enough to what I talk about. Okay, it's there's an incredible history of cyanide and carbon monoxide. Okay, it's and it made me explore the chemistry of these early pioneers. Okay, we want to forget Conrad Dippel and Carl Scheeler is okay. I think one of the greatest chemists of all times. Okay, it's and I thank you.
By now, most of you understand. If you have a question, please come up and stand on the tape, and then from there speak into the microphone. So, are there questions for Steve?
Hi, Steve. So thank you for that. The history was fascinating. What was your initial motivation for studying these compounds?
Well, as I say, when they discovered hydrogenase that had iron bound to carbon monoxide and cyanide, it's we, in fact, I could tell you work where we made compounds that look like that active site. Okay, it's but first when you make a project, you read the literature. Well, in iron cyanide chemistry, you kept going back and back and back. Okay, and it turned out to be marvelous chemistry. And the idea is Diesbach and Dimple, even though they didn't know what they were doing, reacted iron 2 with cyanide. We fell upon the fact, and nobody else had made another compound except Prussian blue or ferrocyanide from doing that very simple reaction. And we discovered by accident, well, just we were forced to try that simple reaction. And it turned out there's a whole area of synthetic chemistry that had not been discovered. And people, it's a lesson. People thought because ferrocyanide is so inert to substitution that when you reacted iron with cyanide, you'd always get ferrocyanide. But if we react to less than 5 equivalents, 6 equivalents of cyanide, we get a whole range of compounds. Okay, and so we discovered this whole area of chemistry, which probably will be my most significant work. Okay, when we retire, the chemistry department puts a plaque on a wall. And it's with your most important discovery. Well, this certainly is going to be my most important discovery if it turns out that my compounds are present on a meteorite and meteors. Okay, it's always your worry that somebody else is going to say, no, we don't see them, but they have pretty convincing evidence. The people found our compounds on a meteorite. So this area just kept getting more and more wonderful. Okay, it's usually, I mean, I've discovered so much more about the chemistry of cyanide. It's been studied continuous for 300 years. I wasn't kidding, where most inorganic chemistry has been done during World War II. Okay, it's not cyanide chemistry, but even 300 years later, we've been able to completely change the field by just doing the simple reactions. Okay, and making a whole range of compounds. And if it turns out these are involved with prebiotic chemistry, it will be wonderful. And I followed my instincts and decided, well, I'm going to study. See, we were interested in the enzymes. Your cyanide and carbon monoxide give very distinctive peaks in the infrared spectra. That's how they discovered they were cyanide and carbon monoxide in the enzymes. So we wanted to learn about the oxidation states affecting iron cyanide stretching frequencies. And we did all that and trying to understand how hydrogenase produces hydrogen. You can make fuel cells. If you can make fuel cells with nickel iron compounds, they'd be a heck of a lot cheaper than using them with platinum. So, but I just came upon this, as I say, wonderful, to me, wonderful, simple chemistry, which a high school student can understand. Okay, we go into a little bit more detail. Okay, and touching on the history of chemistry. Okay, inorganic chemistry. So I think it's neat stuff, and it's as I say.
Can I interrupt you for a second?
Yeah.
I have 3 simple questions that are related,
Yeah.
and maybe a high school student could understand them. One, could you just give a little description of the difference between real chemistry and synthetic chemistry? Second, if these items are on meteorites and are out other places in our universe, then they're not synthetic, they're natural.
Okay. Yes, yes.
And what chemicals were present second before the Big Bang?
Well, there's okay, we'll go back. Before the Big Bang, this stuff comes long after the Big Bang. But still, the asteroid, they believe the asteroid Bennu is unchanged since the beginning of the solar system. So we're talking about billions of years old. And so, yes, I said, do I have to send a correction that we were the first people to make the compound with 2 cyanides, 4 cyanides, and 2 COs? Because if it's been made billions of years ago. Okay, but key, you see, is the fact that they could just be made by just reacting iron with cyanide and water. Okay, and CO. So we call, okay, synthetic chemistry is making something. Now you can make something which has already been made. Okay. But that's a question. Are these compounds minerals? Okay. It's, if they were not made by obviously humans. Okay. It's, so maybe with, and also to look for these compounds, possibly you could look for them someplace on Earth, okay? Because they've been made very simply. Now you need cyanide and carbon monoxide, okay? But it's I say it blows my mind that we could make these compounds so simply, and nobody had done it before. But it turns out they were done billions of years ago, okay? It's and the compounds with 5 cyanides and 1 CO and 4 cyanides and 2 COs, the trans isomers, they're very stable, because if they were going to exist for, billions of years, they have to be pretty stable. Okay. It's now there's also interesting photochemistry. Okay. Which we have studied. Okay. It's so I'm really waiting for this sample from the asteroid to come back to Earth and be tested. Okay, it's because it would be wonderful if these compounds are present on a meteor, on an asteroid. Okay, and they're very careful that their sample is going to come back to Earth without being contaminated. Since I'm not an expert, I worried that the author's going to say, "Oh, we're sorry, we discovered these compounds were contamination," because from meteorites, they're found on the Earth, and if they came in contact, if there was cyanide and carbon monoxide around, they could make them, because they find them in very small amounts. But there are hundreds of organic compounds on these meteorites. These only certain meteorites contain these molecules, but people think that that's one of the sources possibly for prebiotic chemistry. And so,
So to follow up on this, has your work, this discovery of the meteorites, inspired people to look at lava rocks, for example?
well, yeah, it's
Look on Earth for these compounds.
nobody has found anything. Okay, it's but
Not for trying.
yeah, I don't know if they've tried. Okay, it's because exposed to the atmosphere of light. Okay, it's the compounds wouldn't last for a very long time, but it's because they're they're not exceptionally photosensitive, but it's so this is all relatively new. Okay, it's and it exposes you to a whole other class of compound. The geoscientists are the ones who are pushing, exploring the planets and for life. Okay, it's so a lot of them make the case that cyanide is very important. Okay, so we have, of course, everybody knows, and in fact, cyanide has killed millions of people, okay, or has been used to kill millions of people.
So here's another historical sort of question. I'm trying to wake up a sleeping neuron, but I think it was Miller in the 50s did experiments with what was presumed to be the atmosphere of the forming Earth, and put those compounds together with lightning and made building blocks of
Yes.
RNA and DNA, et cetera.
Right, yes.
Might your compounds have been part of his mix?
Okay, that's actually interesting. But it's in fact, it's interesting. Miller and Urey. Miller was a graduate student of Harold Urey, and that was a very important suggestion for prebiotic chemistry. The geologists point to minerals being involved. Okay, it's and so the great thing about being prebiotic chemistry, it's very difficult to prove anything. Okay, it's you can develop chemistry. Okay, and I'm curious if some of these people are going to pick up on using these compounds and to put them into their theories. Okay, it's but the different groups they argue. Okay, it's about Urey and Miller. Okay, thought. I don't think there was no carbon monoxide included in the Urey and Miller, okay, it's experiments. It's I don't think, okay, but I have to look into that. It's but it's interesting because I'm now an emeritus professor, so I had closed down my laboratory, and so this was discovered right at the end of my career, and I go, uh, I want to be able to slowly get my former student involved. Okay, he's a lecturer. Okay, so we're going to at Stony Brook, but he does a lot of teaching. Okay, it's I was going to do a lot of experiments myself, but then I got sick and I have Parkinson's disease, and you don't do chemistry unless you can, with things like cyanide and carbon monoxide, unless you can be very careful. And I can't do that. So I'm trying to get, and you can't just have undergraduates do cyanide and carbon monoxide poison chemistry because it's so dangerous. You have to have well-trained chemistry students. So, but people haven't jumped on this, which is I'm happy because we're going to slowly get back into doing this chemistry. It's with trained students, you can do things with cyanide and carbon monoxide because as chemists, we treat all compounds as extremely dangerous. Okay, so working in fume hoods, okay, and things. And so you can do chemistry with poisonous things very carefully. Okay, but you can't, you have to have people who are trained already before they do these experiments. But as I say, I've learned, my late wife, who was a chemistry professor, accused me of having no hobbies. Okay. My first hobby was chemical information. It's, and then when this came out, all this stuff, I was an expert at searching the literature. And it's wonderful now with Google scanning everything that you can find just about every word ever published. Okay. It's online. Okay. If you search for Prussian blue, you won't find the first synthesis. But if you search for the words Prussian blue in Latin, you find that paper instantaneously. It's so, and you can find lots of interesting things. Okay, we Carl Sheila reports something in his paper which has you react iron with 2 equivalents of cyanide, you get a precipitate. Okay, we have seen the same thing. Nobody has ever proven what that compound is. Okay, so we're working on that. It would be great to have your first reference to Carl Sheila's first report in 1785. It's
I want to thank you, Dr. Koch,
Yeah.
for exploring this area of life that many of us don't know much about.